So thank you very much. I'd like to thank the organisers of the workshop for giving me this opportunity to come back to Cambridge. It's always a pleasure. So today I'd like to talk about understanding some nonlinear interactions in inhomogeneous and anisotropic turbulence. Basically, I'm going to be talking about convection and shear. I'd like to thank my collaborators, primarily Brad Marston, Greg Cheney, Jeff Oishi and Curtis Saxton, who's a postdoc at Leeds. I'm going to be talking about trying to understand nonlinear interactions, and then tomorrow morning's talk by Brad will be trying to put what we've learned into statistical models, or what we call direct statistical simulations, of similar types of fluid flows that I'm going to talk about today. So it's a work that's really talk in two parts. So Brad has agreed to answer all the difficult questions, so please save them for tomorrow. But anything that we say, or most things that Oops. So just a brief outline of the talk. For this audience, I don't think I need to motivate the need to go beyond DNS. The question is where to go. I'm a big fan of reducing models if you can. One way of reducing models is to do statistical simulation, so simulation of the statistics. I'm going to describe this quasilinear approximation, which we've heard about a few times. So when does linearizing about the adjusted, so the fluctuation interactions mean state work? There are certain cases where you can say a priori that this approach is going to work. So if you've derived an asymptotically valid model, like we heard from Pascal this morning or Greg this afternoon, then you tend to have a separation of scales. And in that case, you may derive an asymptotically exact quasilinear approximation. But in general, we're not in the case where we're in the asymptotic regime. We have turbulence coexisting with mean states. So how far can we push this approximation? Can we do better if we generalize the quasilinear approximation? And I'm going to look at two model problems, one of which is anti-diffusive, which is the last one, and one of which I'm really just looking at because I'm going to be able to change a parameter, and the parameter is going to change some of the timescales in my problem and enable me to say something about how good the quasilinear approximation is as one varies certain timescales. Okay. So again, for this audience, I don't think I have to motivate too much, but the flows of AGFD tend to have the coexistence of turbulent flows with mean flows, which tend to vary on larger spatial scales and longer temporal scales. So we've heard a little bit about Jupiter. The solar interior, we have turbulent convection with timescales of about a month, lead to a differential rotation pattern or a shear pattern in the solar interior, which stays largely steady. So this is a result from helioseismology about the internal rotation of the sun. This is driven by turbulence, and the turbulence drives the mean flow, which then coexists peacefully with the turbulence. Usually I don't manage to get to Wednesday afternoon of a conference before somebody mentions the solar cycle. I guess it shows the kind of conferences I go to. But the sun's magnetic field is generated by turbulent interactions, and what you can see here is the solar butterfly diagram, which is the sites at which you see active regions on the sun, and there's this beautiful large-scale mode which shows spatio-temporal order that sunspots are found at mid-latitudes, and then the pattern migrates to the equator, disappears before the next cycle starts. So this is really a large-scale mode interacting with the turbulence, and in fact is driven by fluctuation interactions, we think. And in all these cases, we're talking about rotation leading to a forced symmetry breaking. And so, you know, because these flows are rotating, it knows the difference between east and west. That leads to the existence of a pseudoscalar. And in its most severe interpretation, that's all you need to say for the existence of a large-scale mode. Okay. So there's a natural, once you've broken this symmetry, there's a natural transfer of energy into a large-scale mode, either directly, so via a Reynolds stress in the case of differential rotation, or an EMF in the case of a magnetic field, or via some kind of inverse cascade. And a good question and one which I don't think has been settled is how much energy transfer goes directly into the large-scale mode by so-called non-local interactions, and how much goes via a local inverse cascade. And again, I think that's a very interesting question. So just to make sure we're all on the same page, there are two types of turbulent interactions with means, and the ones that are most familiar to fluid dynamicists who are not geophysical fluid dynamicists is where you put the energy input into the mean flows at large scales, and then the small scales emerge owing to the instability of the large scales, and then the turbulence acts back so as to modify the large scale flows. In a sense, these are easier ones to think about because you have a large scale flow to start off with, and the role of the turbulence is then just to modify the large scale flow. Or you can think of the ones I've described before where the energy input is at small or moderate scales, and then the large scales emerge owing to some kind of correlations in the turbulence, which may appear due to rotational stratification, and those were the ones I was talking about today. And ideally, you'd want a theory, be it statistical or otherwise, which can describe both of these. And of course, we're at an anti-diffusive workshop. I mean, these are kind of usually parameterized by some kind of turbulent diffusion. And if you wanted to kind of parameterize these, you'd need some kind of anti-diffusion or negative diffusion. Okay, so what can you do for model reduction? So what do you do when you have a highly nonlinear partial differential equation that needs to be solved on a vast range of spatial and temporal timescales? Well, if you're an astrophysicist, you just tend to put it on a computer and hope for the best. Or you can construct reduced models that capture the essential dynamics or transitions or statistics. And we've heard a lot about these asymptotic theories. And asymptotic models, if you have a parameter that's very small or very large, the non-dimensional parameters tend to be ratios of either length scales or time scales. You have a separation of scales, and you can derive reduced models, as we've heard about today. Another way of constructing reduced models, which are very popular these days, are so-called data-driven models, data-driven reduced models, where you use simulations to extract, if you like, the most important features. But whatever you do, you really have to treat the different scales on a different footing. And so you can drop certain interactions over some range of scales, okay? And this is an approximation. So if you just do this, if you just say, I'm going to consider all scales, but I'm going to drop some interactions over a range of those scales, then you are doing an approximation, and you only have a limited saving, though you may understand something about the nonlinear interactions, and that's what I'm going to talk about today. You can get some saving by using clever numerical stepping methods, which maybe step over fast scales and input into slow scales, but your saving is limited. Where the real saving is when you calculate the net statistical effect of the approximated range of scales and then project that back onto the full dynamics, so you only have to solve for the large scales. And this would be a significant saving, and that's what Brad is going to talk about tomorrow. So this talk is just going to look at the damage you do by this approximation, or by these approximations, and then Brad is going to talk about the statistical models tomorrow. Okay, so let's start off by talking about what we mean by the quasilinear approximation. And I'm going to have a very general discussion. And the quasilinear approximation involves taking your state variable Q and splitting it up into a formal mean and a fluctuation, doing a Reynolds decomposition. And I'm thinking now of my mean as being a spatial mean, maybe over one coordinate, maybe longitude. Let's focus on longitude. I'll talk about other averaging protocols a bit later. And the quasilinear approximation involves only keeping certain interactions, okay? So we would keep the interaction of a mean with a fluctuation to give us a fluctuation. and we'll keep the fluctuation interactions that give us back the mean. But we're going to get rid of the fluctuation going to other fluctuations. So this is getting rid of any kind of cascade or inverse cascade, local cascade interactions. Okay, and this term here, the fluctuation going to fluctuation going to fluctuation interactions, or eddy going to eddy, the fluids is sometimes called the eddy nonlinearity. And in the context of mean field electrodynamics, Keith Moffat called this the pain in the neck term, the pin term, okay? Now this is an example, if you do this approximation, it's an example of what Craigman called constrained triad decimation in pairs. What this ensures is that you conserve global, linear and quadratic invariance, which is nice. We'd certainly like to do that. But as I said before, there's no local cascade or inverse cascade. Everything is non-local. And just to talk about this, the inhomogeneous anisotropic statistical formulation of this approach will be what Brad is going to call CE2. Now this is a very old approximation. In fact, we did some looking around in the literature, and the approximation we think goes back to Malkus in this paper. This one is in 54. I think this is a rare case where the fluid dynamicists got there before the plasma physicists, which is nice. So this is where Malkus applied the quasilinear approximation to heat transport. And then he did the same thing for the onset the outline of a theory of a turbulent shear flow. And then later, in the 60s, Jack Herring looked at these problems in thermal convection using very similar techniques. In the plasma literature, it's often referred to as the earliest paper being this paper by Vyedinov et al. You can see here it says quasilinear theory. I'm sure your Russian's good enough to see that. And actually, we did some digging around, and there's a slightly later paper, which is called Quasilinear Theory of Plasma Oscillations in an Electric Field. And they say that generalizing some work done by these guys, so this is Fried, Gelman, Jackson, and Wild, and this one goes back to 1959. So again here, quasilinear approximation is also considered. So that's kind of interesting, I think. So what do I mean by quasilinear approximations and when you can use them? Okay, so let's have a look. We have our state variable, Q, and imagine it has a linear part and a nonlinear part. We may have stochastic driving or some other term here, but I'm really just going to look at these operators. And this is all fairly easy to understand. So you take your Q, you split it up into some kind of mean and a fluctuation. You write down an equation for the mean, and so you get an equation that looks like the evolution of the mean, the linear part on the mean, the nonlinear interaction of the mean with itself, and of course the fluctuation projected onto the mean term. So this is, if you were doing fluid dynamics, this would be the Reynolds stress. If you're doing electrodynamics, it'd be the EMF. And then you write down the equations for the fluctuations, and so of course you have dt of q prime, the linear bit, and then you have the terms which look like the mean interacting with the fluctuations in both of its form, and then this term which you get from subtracting the mean term from the full equation, so you get the eddy nonlinearity or the pain in the neck term. And the quasilinear approximation, as I said, involves neglecting this term in favour of some of these other terms. So you can see straight away that if I compare these terms to some of the other terms, I'm going to get some situations where I can neglect this term. So let me just show that again. So this is just the same equation. And imagine we're doing, we have the nonlinear term being the term in the Navier-Stokes equation, the u dot grad u term. So if the fluctuation interaction is small compared with the rate of change of the fluctuations, so in our Navier-Stokes example, it would look like this. Then you get it being satisfied if u prime over some correlation length is very much smaller than correlation time. And this is true if the correlation time is very much smaller than an overturning time. And this we can think of as a Kubo number being very small. So if the Kubo number is very small, then you can neglect the pain in the neck term. Or you can compare this term to essentially the u prime dot grad u bar, and in this case this is essentially an overturning time and a shear time. So if the shear time is very much smaller than overturning time, this is the Strahl number. If that's less than 1, again you can neglect that term. But these conditions are very hard to ensure.
Both should hold, or one of the two?
Oh, one of the two.
One of the two.
It's very hard to ensure that this is true a priori, right? Because it involves correlation lengths of your turbulence, correlation times of your turbulence. Unless you're in some asymptotic regime, then you can't guarantee that this is going to happen. But these are also crude estimates, right? Because really, you want to know the effect of not the, let me just go back. It may be that this term is not small, but its projection back onto the mean is small, okay? So this term might be large, but for some reason when you project it back onto the mean, that projection is small. What's certainly true is that if this is small, then its projection back onto the mean is small. But it may be that this is not small, but its projection back onto the mean is small. So you really need to test these things out. So you can have, so for example, you can have your fluctuation looking like a bit which is driven by the pain in the neck term, which is not small, and a bit which is driven by all your other terms. But when you project back on to the means, then the pain in the neck term doesn't actually have any effect. And in order to understand this, you really need to evaluate really how much energy is being transported by the various mechanisms. And so you need to evaluate transfer functions, which is something that is regularly done. Okay. So one other way of thinking about this Kubo number, if you like, it's a measure. Unfortunately, it's an a posteriori measure of how much transfer is being done non-locally versus how much transfer is being done locally in the cascade. So how much is you're directly changing the mean flow versus how much is in an inverse cascade. Okay. So as I say, you can ensure that these things are small if you have an asymptotic separation of scales, or, for example, if the turbulence is, you know that the turbulence is decorrelating on a fast time scale, which it could be. It could be. Okay. If you're allowed to use the quasilinear approximation, which we'll investigate, then, as I've put down here, the means adjust only owing to perturbation going to mean interactions. Okay? And the perturbations respond only to the mean. And what's vital is that the equation for the perturbations is linear in the perturbations, in the fluctuations, sorry. So it's quasi-linear because the mean is evolving, but the equation for the fluctuations is a linear equation, and therefore it's amenable to closure, as we'll talk about right at the end. So anything we do, we'd actually like to keep that property. So one of the things a few years ago we decided to do was just extend this definition of the quasi-linear approximation. We just generalize it. Instead of talking about formal means and fluctuations, we'll just generalize it to something which has large scales and small scales. So this range of scales idea, and we're going to just treat them on a different footing. And we're going to have a cutoff between the two ranges of scales at some wave number lambda. So if lambda was equal to 0, then we'd have a formal mean and our fluctuations again. But if we can allow lambda to be a non-zero wave number, in which case we're kind of generalizing the quasi-linear approximation. So this is something Brad, Greg and I did, gosh, nearly 10 years ago. And so what we do is we consider all wave numbers less than some cutoff, or less than or equal to some cutoff wave number lambda, as our large scales, or low modes we call them. And we kept certain interactions such that we respected Craigman's triad decimation in pairs. So the interactions we're allowed to keep are the low interacting with the low going to a low. That was a trivial interaction that we had before. We're going to keep the low interacting with a high mode to give a high. And we're going to keep the very important high interacting with a high to give us a low. But we're going to get rid of all these other interactions. So this is the high going to high, which we got rid of before. But in order to conserve quadratic invariance, you need to take these out in pairs as well. And so this is the low going to high, and the low high going to low. These are very few interactions in general.
But it's non-resonant. I mean, the left two in the lower row, they are non-resonant, so you probably could neglect them.
Yeah, in general, there's no problem. I mean, and there's been some recent work with people who've put them back in. If you put them, both of them back in, you're okay. But it makes very little difference. Okay, but what is key here, and why this is a slightly better approximation than just a pure quasilinear one, is that before, okay, let me go back. Oh, I went back too far. Here, if I've got, say, m equals 10 as my high mode, then it interacts with an m equals minus 10 to give me an m equals 0 mode. There is no mechanism for 10 to put energy into 11. Okay, it can really only put energy into 0 or put it back into 10 by interacting with 0. However, if I include more modes in my mean, in my large scale, then imagine I've got here a 10 interacting with a 1, because a 1 is now in my large scale, and so that can put energy into an 11. I could get my 11 interacting with the 1, put it back into 12, and so I can put energy down to the dissipative scale by continually scattering back off the mean. Okay, so energy can be scattered into the low modes via interactions of the short at different wave numbers. And that turns out to actually make that a better approximation, as we'll see. One thing I'd like to stress is that we've still got an equation which is linear in the high modes, and so it's still amenable to closure. So this is the generalized quasi-linear approximation. So I'm going to just see how well these things do on two paradigm problem. So I'm not going to do any statistical simulation. I'm just going to essentially just take out certain triad interactions and see how well we do at approximating full DNS for two problems. The first problem I'm going to look at is a nice paradigm problem of convection with a thermal wind. And so this is not an example of anti-diffusive behaviour. We're just going to have convection, we're going to have a shear flow, which is driven by the interaction of temperature gradients with rotation. And because we can change the strength of the shear flow by changing a parameter, we can vary the various timescales that I talked about before in a systematic way. The second problem I'm going to talk about is a simple model of the generation of jets in Jupiter called the Busse Annulus. It's the interaction of convection with rotation to drive mean flows. This is one where the mean flows are driven by an instability, and the instability is convection. We've heard some talks about instabilities at very small scales driving systematic flows. This is an instability of convection driving systematic flows. And because the large-scale systematic flows can act back on the method of putting energy in, you can get some very interesting dynamics, which I'll talk about, and we're going to be interested in how well quasi-linear type models capture this behaviour. And then tomorrow, Brad will talk about how well direct statistical simulation can capture some of the behaviour you've got. So let me start with this. So this is three-dimensional rotating convection with a thermal wind. So we've heard a lot about convection. So in usual convection, Rayleigh-Benard convection, you have a temperature gradient in Z, which drives the convection. So you have hot at the bottom and cold at the top. We're also, in this model, we're going to have what we think of as a latitudinal temperature gradient. Okay, so we have a gradient. The temperature depends linearly on this coordinate y. And it's this that is going to drive the shear flow, because when you have a gradient in y, then you have to have what's called a thermal wind. And the thermal wind, the strength of the thermal wind depends in collaboration with the rotation. Sorry, because you're in a rotating system, the strength of the thermal wind depends on this temperature gradient, Ty. Okay. So we have various non-dimensional parameters. We have Ty, which actually has been things have been non-dimensionalized here. So we have the Taylor number, which is a measure of the rotation. It's 1 over the Ekman number squared. The Rayleigh number, which is a measure of the thermal driving, and the Prandtl number. Okay, and this setup was originally looked at by Hathaway et al. In 1980, and also it's been looked at extensively by Laura Curry in a thesis, which was 10 years ago, Laura. There you go. Just to make you feel old as well. Okay, so we solved the equations for the perturbations, the fully nonlinear perturbations to the basic state. Okay, so these are the equations. You see we have this linear shear flow, which is doing advecting of both velocity and temperature. We have thermal driving. Here are nonlinear terms. Okay, and one thing to note is that turbulence can extract energy from both the temperature gradient directly or from the shear if Ty is non-zero. So a question then is, how well does QL or GQL do as Ty changes and the shear increases? So if we start off with Ty equals 0, we just have rotating convection, and one wouldn't necessarily expect quasilinear theories to do very well. In fact, you know, Malthus's original theory was, well, for straight convection, but there's no real reason to assume that QL or GQL would do very well, and indeed it doesn't. But does it do better as we increase Ty?
It's periodic boundary condition in this?
Yeah, sorry, I should have said. Yeah, periodic boundary conditions in both horizontal directions, of the perturbations in both horizontal directions, and fixed temperature and stress-free in Z. Okay, so here are some solutions. This is the vorticity out of the plane for different Ty's and Rayleigh numbers. So this is a fairly laminar state. This is just rotating convection. This is a more turbulent state, again, for rotating convection. And then as we increase Ty, or the amplitude of Ty, we start to get the sheared structure. And again, as you increase the Rayleigh number, you get smaller and smaller length scales, thinner plumes, which are being sheared out. But what I want to stress is, as I change Ty, I'm going to be changing the timescales. So let's have a look at what the timescales do. So you can just go in and calculate the 3 timescales of the problem. So you can calculate the overturning time, the correlation time of the turbulence, and the shear time. Okay, I'm going to start with the non-sheared case. So for the non-sheared case, you get very weak shear flows. They're not very systematic at all. They're not like the solutions that David showed the other day with the very strong winds. We don't have any of those. The correlation time is of a similar order to the overturning time. This is well known for convection. Eddies tend to go around once before they decorrelated, about once. And the shear time, these are very weak shears, is much, much longer. So none of the conditions that we've set for the quasilinear approximation to work are met. So let's go to okay, this is going to be somewhere in the middle. Let's go to the far end where we have the strongest shear. You can see that now the shear time has dropped down to be the quickest time. So we have a very strong shear. Actually, now the correlation time is shorter than the turnover time. And this is because the eddies get sheared apart before they can do a whole circle. So the shear is strong enough to decorrelate the eddies before they can do one circle. And for the Ty equals minus 0.5, it's somewhere in the middle, it's an intermediate shear. The shear time is of the same order, or pretty much of the same order as everything else. I think it's very hard. You can maybe say the shear time is slightly less.
Is the correlation time geometric mean between these two?
Is the I don't know.
Check it.
Okay. Okay. Yes, boss. Will do. Okay. Who was it who said about having a PhD supervisor kind of shouting in their head? You weren't even my PhD supervisor. Okay. Okay. So let's now take some of these and see how well the quasilinear approximations do. So the first thing I'm just going to plot a time series of the kinetic energy. Okay, so let's start off over here. So this is just rotating convection, and we're going to do the quasilinear approximation. So that's where we put this cutoff between mean and fluctuations at wave number 0. And then we're going to do different flavours of the generalised quasilinear approximation, moving the cutoff to larger and larger wave numbers, smaller and smaller scales. And what you see here, and we'll see it again in the means, is that the quasilinear approximation vastly overestimates the amount of kinetic energy. DNS is black, so we're going to be matching to this thing here. So the quasilinear approximation vastly overestimates the amount of energy in the turbulence. As you increase the degree of the approximation by making lambda bigger and bigger, eventually you get the right answer, but only by really lambda equals 10. Okay, so this is an example of the generalized quasilinear approximation not working that well, I think I would say. Okay, let's go to the one over here, or over here on the strong right-hand side, where I think things work a bit better. It's still true that the quasilinear approximation in both cases massively overestimates the energy in the flow, but the generalized quasilinear approximation, I think it's fair to say, does pretty well. It does pretty well, and you might expect it to do pretty well because we've set it up such that we've got the timescales in the right ordering. And I think it's fair to say in the intermediate case, it does intermediately well. Okay, so that's just the energy, but what about the means, which is kind of what we're interested in, the large scales? Okay, so this is just showing how the kinetic energy over the DNS kinetic energy changes as I change this cutoff, and you can see that the sheared cases, you have to get to smaller lambda to get the right answer. Okay, how well does it do in getting the mean shear? Well, all of the quasilinear approximations, until you get to lambda equals 10, again, DNS is in black, so you want to look for the black curve. They do very poorly, I think it's fair to say. In fact, the quasilinear approximation is kind of all over the place. By the time you get to Ty equals minus 2, then even lambda equals 1 is having a good stab at getting the shape of the mean. This mean has been averaged over time as well as the horizontal directions. Okay. Now, why is that? Again, I said you have to look at transfer functions. So we looked at the transfer functions as calculated in these papers for full DNS and quasilinear and generalized quasilinear. And what you can see is that when Ty equals 0, essentially all energy is transferred by local local interactions. So there's an inverse, there's a cascade, and it's really K and K plus 1. It's K putting energy into K plus 1, essentially, all the way down. Okay? And this is impossible to capture in the quasilinear approximation. You can capture some of it in the generalized quasilinear approximation, essentially through this process of scattering off a mean. So you can put energy from 10 into 11 by scattering off 1. But when Ty is minus 2, the dominant energy transfer is directly into and out of the mean. You can see the strongest red and strongest blue are in these mean flows, and the linear and the cascade is subdominant. And so this is fairly easy to capture via even the quasi-linear approximation gets most of the energy transfer correct. Okay, so that was really trying to understand what happens when you can very carefully control the strength of the shear. What happens in a case where the strength of the shear emerges as an output of your model. So that's the second problem I'm going to look at. So, well, I don't need to motivate this. So we're interested in explaining the very quasi-steady jets on Jupiter. There were two competing theories for the driving of these jets. I think it's possibly fairly settled now. But let me just tell you what the two competing theories were. One was that the jets were driven in a shallow layer, very close, shallow atmospheric layer, close to the surface. And so you have a thin layer, stratified flow, you have 2D dynamics, kind of shallow water type dynamics, and the 2D coupled with the beta effect, the variation of the Coriolis force with latitude, would lead to the natural driving of zonal jets. And so there are some very nice models based on this. The second paradigm, if you like, is that the jets are driven kind of deep via convection, and the kind of quasi-2D dynamics arises from not stratification but rapid rotation. So rapid rotation, as we've heard, and I'll show you some pictures. Oh, in fact, why don't I just show you some pictures? Wants to align turbulence with the rotation axis. So this is a heroic calculation by Thomas Gastin of convection in a rapidly rotating spherical shell. And what you can see here is that the convection cells, they're small in this distance, but they're elongated. They tend to be independent of this coordinate z, and so your dynamics is quasi-2D in the sense of there's very little variation in z, okay, aligned with the rotation axis. And the simplest, I think the simplest model you can think of, which captures the dynamics of this very complicated situation, was proposed by Busse in 1976. And the idea was to try and get a two-dimensional model, and he did this by essentially considering a cylindrical annulus. So he kind of cut out from the spherical shell. You have an inner and an outer cylinder, okay? And in order to capture the effects of the fact that of geometry, the fact that we're going from kind of longer columns to shorter columns, he put on a linear boundary. And so when you take this system, this so-called Busse Annulus system, and you take the equations and you integrate, you write down equations for the integrated velocity over z, and you apply the boundary conditions at the top and bottom, you can derive, and I'm not going to go into any detail about how to do this, you can have a look at Busse's paper, you can derive a set of equations which are asymptotically valid in the limit of rapid rotation, and the equations set you get, okay, looks very much like the equation sets we've been looking at all this week. So let me just explain. Zeta is going to be the vertical component of the vorticity. It gets advected, size a stream function. This is the beta effect term. The beta effect term comes in through the regular beta effect, that columns, when they move out, they have to shrink because of the geometry. But in this case, we're thermally driving. We're not stochastically driving like we've seen in some of the other talks. So we're thermally driving. We have a friction, and we have regular viscosity. See, beta is a measure of the slope of these end walls. And then we have to keep track of the temperature, of course. So we have an evolution equation for the temperature perturbation, which just looks like regular convection. So we have convection. The convection drives the vorticity, but be aware that the vorticity is going to act back through the stream function on the convection. So this is really a case where you have large-scale flows driven by an instability. And so, as I've said here, convection interacts with rotation to give us a Reynolds stress, which leads to zonal shear flows, which we'll see in a minute. That acts back on the convection, and of course, that can modify the Reynolds stress. So as the convective driving is increased, convection will set in. The convection cells interact with the rotation via the beta effect to drive these shear flows, or you can think of them as thermally driven Rossby waves. We saw some other examples of Rossby waves driven by instabilities before. These turbulent eddies with correlations lead to the Reynolds stress. The shear acts back, and it can act back either by just essentially suppressing the instability in a kind of gentle manner, or you can get what's called predator-prey dynamics, and we'll see examples of that later on. So let me just show you some examples of the dynamics that you can get, depending on the parameters. And there's a very nice paper by Chris Jones here, which maps out where you might expect to get all of this kind of behaviour. The one to keep an eye on in the movie is this one. This is the zonal velocity. Okay, I'm just going to show you what happens. And this is the temperature here. So for this case, you can see the zonal velocity is driving jets, and in this case we get, well, it's easy to see over here. If you average over x, you can plot a Hofmöller diagram of the zonal velocity against y and time. You get these bands of prograde and retrograde jets, and in this case you get 7 jets for these parameters. You can get jets on the large scale or small scale jets, again depending on the rotation rate and the friction. Okay, so that's one type of behaviour we'd like to see how well QL and GQL do in describing. A more interesting type of behaviour, I think it's fair to say, is this one, where we get this kind of predator-prey type dynamic. So again, keep an eye on the second one, because I think it's clearest there. I'll play this movie twice. So originally it wants to put 3 large jets in. That's coming up to here. And then it decides actually that's the wrong wavelength. So one of these jets is going to disappear in a minute. So now we've got 2 jets, but that 2 jets is not quite the right wavelength either. And now we get this kind of bursting behaviour. This is what we call the predator-prey dynamics. So the convection drives the shear switches off the convection, and because it's switched off the convection, there's no energy input into the shear, and you get this predator-prey type system. And if you look at the Hofmöller plot, you can see these things.
Steve, how sensitive is this to the aspect ratio?
Oh, quite sensitive. Yeah. Absolutely, because you have to fit the right, yeah. But you can find it for, you'll find it in different parameter regimes for different aspect ratios, right? It's whether you can fit n and then, yeah, plus 1. So I'm running out of time, so let me just say how well these quasilinear type theories do. It turns out that for these, so this is, remind you, this is just DNS. quasilinear theory, you do get jets driven, but you get the wrong number of jets. We couldn't get quasilinear theory to get this right. But as soon as you go to generalized quasilinear approximation with just one wave number included in the large scale modes, you do get the right answer. And by the time you get to 5, you're even getting some of the variability of the jets correct. Let me just show you the more difficult case, which is the bursting. Both quasilinear and GQL with lambda equals 1 get nowhere near. And you have to go to lambda equals 5 before you can see the bursting. I'm running out of time, but just let me remind you that the generalized quasilinear approximation can lead to a closure for direct statistical simulation, which I think is going to be a more accurate one than CE2, for those of you who know what CE2 is. I'm not going to say very much about it because Brad is going to talk about that tomorrow. So let me just finish with my conclusions. So the quasilinear approximation, it can be valid in cases where the projection of what we call the third cumulant onto the second cumulant equation is small. It's very difficult to know when that's going to occur a priori. A better approximation than QL is GQL, which just generalizes the definition of mean to large scales. It's nice because it allows for scattering of energy from eddies at one scale to another via the large scales, and it still conserves quadratic invariance, and it can form the basis of a statistical closure. I think it's fair to say there are lots of things we don't understand. There are many open questions, so I'll just finish by saying what some of them are. There is a kind of equivalent of generalized quasilinear approximation, but in the time domain. It's a so-called self-consistent method, which emerged from some work done by Lorette and Dwight, this RZIF property, and we're still trying to understand the relationship between GQL and this self-consistent method. I've really talked about spatial averaging, but it's very interesting to think about the role of different averaging procedures and relationships of zonal averaging to ensemble averaging. Ensemble averaging works better in most cases, but in an ergodic system they should be the same. So thinking about when these systems are ergodic and when they're not is an interesting question. An interesting thing to think about is, can this approach be combined with data-driven modelling? We want to go beyond quasi-linearity. What's the minimal thing we can put in to go beyond quasi-linearity? Can some kind of data-driven method tell us that? These approximations are used as a basis for the derivation of statistical theories. It seems, do these theories work better in the case of an inverse transfer of energy, even away from equilibrium? I don't know. We have some ideas about going to beyond quasi-linearity. I'll just finish by saying, how do these model reduction methods work on climate problems that involve strong layering? So if you're here at the end of May, I'll talk about that. So thank you for your attention.
Very much, and thank you for the effort for tomorrow morning's talk to motivation for everyone to get up at 9 AM.
Thank you, Steve. Very nice. Am I right in saying that your approximations mean that the small scale flows obey a linear equation?
Yeah.
So what's to stop it running away?
Adjusting, the mean adjusts such
But
that...
how can you be sure?
That's a good question. So there are various ways of solving these systems. I didn't talk really about how you can solve the systems. So one way of solving these systems is to look for when, it's a linear system, you can do an eigenvalue problem for the small scales, and then you want to find the large scales that give you a zero real part of the growth rate. That's one way of doing it. And that, Greg Cheney and Guillaume Michel, yeah, they have a very nice way of doing it. There are other methods for doing it. In general, I don't think you can, because you might not capture, the mean may not evolve fast enough to stop the small scales.
So you can't guarantee it, but it seems to work.
If you just use I don't. If you just use a regular time stepping method, you can't guarantee it. Yeah.
So, sorry to be troublesome, but you know, a crucial element in the fundamental development of the theory in plasma was the realization of resonant and non-resonant particles.
Yeah.
I mean, that leads to, and it's somewhat related to Mike's question, it leads to that sort of underpins issues of can you get a really dynamically stationary state.
Yeah.
And I think in particular the origin of irreversibility in the system, which I would say swept under the rug rather in your discussions. I'm wondering if you could comment on all that.
So I think that's a really important point, and thank you for being troublesome. So the question is, what is the minimal amount of irreducibility you need to, irreversibility you need to put in to improve these methods?
It's not a put in, right? It's a point if you have overlapping resonance, you get stochastic particle orbits in the Vlasov problem, and off you go.
And in the fluid problem, it's there. Of course, there's the higher order terms. It's there. The question is, what do you need? Because I mean, you'll see tomorrow. You can put in the next term in the cumulant expansion, but that's a very expensive thing to do.
But then the next term can involve higher order interactions, which go, etc., which then you're resting on that to save the ship, as it were.
Yeah, I agree. So I'll just say, as I said earlier, Brad is going to answer all the hard questions. But it's true. Exactly what you say is true.
Sorry.
No, you're absolutely right.
It's different here.
If you have separation of time scales between the perturbation and the mean, but spatial overlap between them, can we still use this quasi-linear or generalized quasi-linear theory?
Yes. Yes, you can. In fact, that's quite a good. I think that's where it works quite well. If you have separation of time scales, but no separation of spatial scales. Because I haven't assumed any separation of spatial scales. I've just done the.
But you can have very local transfers in the ones that you don't neglect. You can still have like perturbation interacting at the similar scale with the mean.
My feeling in that case is you'd probably want to start off by doing, if you do have a separation of timescales, you would start off by doing, a method of multiple timescales first and deriving a reduced set of equations, and then I would go off and do then you've got something. You're saying you haven't got any separation of spatial scales, so then you have to do something, with the spatial scales, but something like this, yeah.
One more question? I don't know. We've got two now.
So at some point you showed these transfer functions where the energy was going from k-1 to k+1. So why didn't your quasilinear theory have any transfer? You have scattering, right? You have
the GQL did. The GQL did. Sorry.
No, but I'm talking about the actual pure quasilinear theory. It still has interactions with the mean, so the mean can scatter the fluctuations.
These are horizontal transfer functions.
Okay.
So there's no. Yeah, sorry. Yeah, thank you. Yeah, sure.
As maybe short comment. In one most trivial case, which we kind of solved and Anna wrote a review on it, namely that in inverse cascade in 2D you have this big vortex or dipole, and we see that quasi-linear approximation works in some special domain.
Yeah.
Outside cubic dominates, and still nobody solves the matching problem how to match two, but at least this is a kind of mental picture I always have. This is something which works somewhere.
Yeah.
And then you need to match it with other, which would be already great.
Yeah.
And it describes also special fluxes.
I mean, for the problem with the vortex, people have done the next order down, which is C3, assuming certain symmetries. But I don't think you need to go that far.
Okay, time to bring the session to a close, and thanks Steve again. Thanks very much.